Hello, everyone. I'm going to be presenting our work on Coalitional Framework for Network Centrality. It's a paper that is due to appear soon in the Proceedings of AAMAS' 2020, and it's joint work with my colleagues Cosmin Bonkish and Claudiu Gădina. Okay, so what we do in a nutshell is we study representing centrality measures in social networks by coalitional game theory. More precisely, we consider using so-called succinct frameworks for representing coalitional games, and we concentrate on one framework which is able to incorporate skills and tasks into centrality measures. And this representation provides also some application to modeling a phenomenon we call helping centrality. And helping centrality refers to the extent to which an agent is able to summon its friends to help a certain coalition achieve some tasks by the skills of its friends, not by its own skills. And the paper has more technical results than the ones that I'm able to present here. So please take a look at the paper as well. So the setting is one which is very familiar. It's a setting of centrality measures in social networks. And here is a well-known picture of marriage families in Florence by John Paget. And as you can see, the Medici family is quite central. And people have been working quite a bit to measure and formalize the notion of centrality in a social network. And they proposed hundreds of measures of centrality. Degree centrality, of course, it's the most important one, but there are other ones like closeness centrality, and ones which we're going to be concerned with, like between centrality and eigenvector centrality in this paper. So what is degree centrality? Basically, it's a rescaled version of a degree. So the centrality of a node y is 1 over n minus 1 times its degree. And it's done like that so that the centrality of a node is between 0 and 1. Between centrality has a slightly more complicated definition. And the idea is the following. We're looking at shortest paths between nodes x and z. And we're computing the percentage of shortest paths between x and z that go through y. And summing up this ratio over all pairs x and z gives us what's known as between the centrality of node y. Eigenvector centrality has an algebraic definition. So we start with the adjacency matrix of the graph, and we compute the largest eigenvalue and the eigenvector corresponding to this largest eigenvalue. And if we suitably normalize this one, then the component corresponding to node y is what's known as the eigenvector centrality of node y. So if you want to know more about measures of centrality, I've listed here two references. One is from the standpoint of algorithmic/computer science, and the second one is more with an economic bent. Okay. So that's as much as I can say for now about centrality measures. And sort of the main theme, the main thesis that we wanted to defend in this presentation is the following. People are often studying network centrality as if it was a purely graph theoretical phenomenon. But if you think about things like degree centrality or between centrality, behind every motivation for defining a measure, there is an informal story which talks about the capacity of the node to act, to do things. For instance, for degree centrality, the fact that we care about the number of edges has to do with the fact it's how many nodes is the agent able to directly contact. Whereas between centrality talks about the capacity of the node to block flow in the graph which is flowing across shortest paths. And the more central in the sense of between a centrality and node is, the more the node is able to intercept such flows. So the point is that uh, centrality should really be about what agents are able to do as a result of their position, and not only that. So it's not merely a graph theoretical notion, but it correlates somehow with the ability of influencing, of acting. And of course, the natural question is, how do we model this? And our proposal is to use a framework from coalitional game theory, more precisely what's known as the succinct framework. Okay, so that's our conclusion. So just to be on the same page, let me give you a 1-minute course on game theory. We start with what's known as a coalitional game. So we have a set of players and the valuation function. And this function associates to each set of agents a value that these players are able to guarantee for themselves if they associate, no matter what the other ones are doing. For instance, the simplest example may be you take a voting game with 3 players and a coalition that has majority. In this case, it's 2-player wins because it can impose its will. So as you can see, the value of coalitions 1, 2, 2, 3, 1, 3, and 1, 2, 3 is 1, and all the other ones have value 0. And many times we assume that the grand coalition forms, that is, all players eventually associate to cooperate. And one of the important question is, how do you divide fairly the payoff of the grand coalition among members of the agents society? And of course, there is a standard answer for that, the well-known Shapley value. And the idea of Shapley value is that we're averaging over all ordered coalitions the marginal contribution of node I. That is, we consider some players in some order, and the marginal contribution of player I is the difference between the coalition up to the moment when I joins, including I, and the coalition, the value of the coalition before I joined. And of course, we average it because this would depend on the actual ordering. So this is a well-known way to fairly divide payoff, and we're going to use it. So we're actually going to consider a setting which merges social networks with game playing. So in our setting, we have players in a coalitional game are also nodes of some network. And we would like to set up the game in such a way that notions of centrality arise as a Shapley value of the associated game. So to give one such example, consider the following game. The value of a coalition of nodes is the number of nodes in the coalition plus the number of neighbors. This is a game that's been studied for quite some time. For instance, by Suri and Narahari in AAMAS 2008. And the associated Shapley value is known by the name of game theoretic network centrality, and it has a very nice closed form formula, and it's been used recently in studies on identifying important actors in terrorist networks. So this is just one example of a measure which could be defined without reference to game theory, but it could also be defined by resorting to the Shapley value of some game. Okay, and a natural question is, are all centrality measures the Shapley value of some game? This is not a question that we answer because the answer is already known. The answer is yes, but the result is somewhat artificial, and it doesn't really have good applicability anyway. It's somewhat artificial because, in a certain sense, the game, in the proof of this result, builds in the centrality within the specification of the game. Okay, and it's not practical anyway because, as you saw before, to give a coalitional game, we would have to specify 2 to the n values corresponding to all the coalitions anyway. So we're not going to be concerned with coalitional game in general form. Instead, we're going to be considering what's known as succinct game theoretic representation frameworks. And coming back to the thesis that we um, defended earlier, we want to concentrate on one specific framework which explicitly represents skills and tasks within the specification of the game. So we're going to actually study one such framework where what a player is able to do is explicitly represented, and the value of the player arises from that representation. And it's a framework that's been studied before, again, in the agents literature by the name of coalitional skill games. And the coalitional skill game is a three-tuple. We have a set of agents, we have a set of skills, and each agent is endowed with some subset of the total set of skills. And then we have a set of tasks. And each task is basically a multi-set of skills. In Bacharach et al., it's a set, but we can extend it slightly to require a multi-set of skills. And that's basically because some tasks will require multiple agents to have a certain skill. On the other hand, we're going to assume that an agent doesn't have multiple copies of a skill. So a task may require multiple agents with some skill, and a task will yield some profit. And now we can totally specify the value of a coalition as follows. We take all the tasks, and for a specific coalition S, we see if the members of S have enough skills to fulfill the requirements of task T. And if that's the case, then we add P of PT. If not, it's 0. So we sum up over all tasks that could be accomplished by the coalition. And Bacharach et al. Proved that, in a certain sense, every monotone coalitional game can be simulated by a coalitional skill game. So this is a framework which is succinct because we're only giving skills and tasks, and the value arises implicitly. On the other hand, it's rich enough to, represent most natural coalitional games. Let me give you just one example of a coalitional skill game. And this is a setting that is inspired by a paper by Michalak et al. And it has to do with nodes in terrace networks. So we have a network here that corresponds to the network of terrorists on the 9/11 attack, as reconstructed by Valdez-Krebs in 2002. And the scenario that we're going to consider is a version of the one that Michalak et al. Considered. Namely, nodes may have one of the following skills: being a pilot, having or knowing martial arts. And in this setting, a node will have at most one skill, if any. And the color of the nodes represents what skill the node has. And we're going to say that a coalition S can carry an attack if it contains at least 2 nodes which know martial arts, and at least 1 pilot. Okay, so this is a reason for considering this multi-set extension of coalitional skill games, because we want to be able to state that you have at least 2 agents with capacity M. And of course, representing this scenario as a coalitional skill game is very easy. Players are the nodes. We have 2 skills, P and M. We have 1 task, attack, which is a multiset of P and two M's. And the value of a coalition T is 1 if T can attack and 0 otherwise. Okay, so this is a very simple example of a coalitional skill game. Incidentally, I'm not going to assume, for the purposes of this paper, that coalitions need to be connected. Of course, one can add such restrictions, and in reality, that would be something natural to add, and then we would be using the Meyerson value instead of Shapley value. But for now, I will assume that a coalition has value 1 irrespective of its topology. Okay, so this is only for technical convenience and for making the point that we wanted to make. So, what are we interested in? We're interested in representing every centrality measure as a Shapley value of some coalitional skill game. And the natural first question is, can we always do that? A second question is, does that help us in any way? And as you can see, there is an answer, which is yes, in the form of a fixed parameter tractability result. So we've shown that there are computational advantages. Now, another orthogonal question is, can we use this framework for anything interesting? Can we model something that wouldn't be possible to model without a game theoretic framework? And we argue that helping is an example, and we're going to be talking about helping in the second part of the paper. For now, let me devote basically like a few moments to give one example, and that's how do we represent degree centrality as the Shapley value of a coalitional skill game. Of course, we're not going to really do degree centrality, but degree. It's the same up to a multiplicative factor. So for us, players are going to be the nodes. Skills will correspond to edges, and a node will have a skill if it's adjacent to the edge. Intuitively, a node can have the skills of the edges it's adjacent to. And tasks are also edges, and each edge comes with a profit of 2. Intuitively, to complete a task, you have to cover the edge, basically. So you have to have at least one of its endpoints in a coalition. So the value of a coalition is the number of edges covered by vertices in S. And it's a very simple exercise to prove that the Shapley value of this coalitional game will basically divide the profit of each edge equally between its endpoints. So then each vertex gets 1 from each edge it's adjacent to, and then the Shapley value is the number of neighbors, that is the degree. Okay, so it's fairly easy to represent degree centrality as a Shapley value of some coalitional game, and degree centrality, I would say it's not the only one. We have more examples in the paper. So let me start with one result which answers the second question, and I'm not going to really spend too much time on it because the details aren't necessarily very exciting. And the result says that if we take a coalitional skill game, and we parameterize the complexity of computing the Shapley value by the largest number of skills needed for every task, for some tasks that is, then computing the Shapley value is fixed parameter retractable. That is, there is a polynomial time algorithm whose complexity may be exponential in k, but it's polynomial in the size of the game. And the proof of this result goes by dynamic programming, by constructing a table whose columns are the subsets of skills. Remember that a task is a multi-set of skills. So we take all the subsets, that's why we have to do the k, and we compute basically the probability that an agent is critical by filling up this this table. And sort of an application of this result is the fact that if you can represent centrality measures within some bound k, then all such measures can be computed in polynomial time via a single algorithm, the one that we've just described. Okay, so we don't really need to argue that such measures have polynomial time, are computable in polynomial time. They're computable in polynomial time by one canonical algorithm. So this is as much as I'm going to be talking about this aspect. So in conclusion, there are some computational advantages about representing centralities by coalitional skill games. So let me go to the first question, which is, can we represent every centrality measure as a Shapley value of a coalitional skill game? Now, we would expect, in line with the Bacharach result before, that the answer is yes. And indeed, our first theorem states that the answer is yes. Every centrality measure is a Shapley value of a coalitional skill game. There is one problem, which the proof of our result shares with the original proof, that basically this representation is highly artificial, and it's bad in the sense that we're actually constructing the coalitional scale game by building into its profits the computed values of the centrality. So in a certain sense, although the answer is yes, in a way it feels like cheating. So a natural question is, can one preclude this? And what's the answer if we preclude doing something like this? And the answer is no. If we impose some sort of restriction on how we can build this game, then there are some centrality measures that cannot be represented in this natural sense as a Shapley value of a coalitional skill game. And sort of this intuition is that we want to formalize the following idea, that the value of a coalition depends in a simple manner on the network structure without having to go for computing centralities and all the other stuff. So we're going to make this a little bit more precise, but the intuition is that we want to avoid the kind of cheating in the first result. So we're going to give a formal framework a little bit later, but let me state that in this framework, degree centrality, between centrality, game theoretic centrality are fall within this restriction that the value of a coalition depends in a simple manner on the network structure, but eigenvector centrality doesn't. Okay, so this is how we prove our result. So let me give first some visual intuition. As I said, we have the informal notion of centralities whose game representation depends simply on the network structure, and that's an imprecise notion. And instead, we put something that is larger and which is mathematically precise and captures all these three measures, but which doesn't capture eigenvector centrality. So let me actually give some more details about what this notion of a rational centrality measure is. And it's actually something very simple. What we're going to do is the following. We're going to first encode edges, potential edges that is, in a graph, as well as vertices, by two sets of Boolean variables, xw for potential edges and yv for potential vertices. In the following sense, we're going to, for instance, we're going to encode the fact that we have a set of vertices in a coalition by putting a 1 for the corresponding variables. Okay? And the centrality measure C is called rational if it basically can be represented as the ratio of two polynomials with rational coefficients in the variables corresponding to the edges. So in this sense, basically the actual centrality depends in a very simple and restricted way on the on the graph topology, because the edges correspond to the variables and the polynomials are fixed. Although, as you can see, the definition is quite weak because we allow these polynomials to vary from from vertex to vertex. So it's not one polynomial for all the vertices. For each vertex and a certain value n, we require that this happens independently of the graph. Okay, so this is a notion of a rational centrality measure. And the punchline will be that eigenvector centrality is not rational. And the proof for this is actually quite simple, is that there are some simple graphs whose eigenvector centrality is an irrational number, but the quotient of two polynomials with rational coefficients should give a rational centrality, a rational value for the centrality measure. Just for an example, let's look at degree centrality and argue that degree centrality is rational. And here you have the polynomials. As I said, the polynomials may depend on the vertex. So basically for vertex V, we sum all the variables corresponding to the edges which are adjacent to V, and we get a polynomial Pnv, and of course Qn is 1. So again, up to normalization, this is degree centrality. We can also prove, and I'm going to actually show it to you, that between centrality is a rational centrality measure. And for that, we do the following. For every pair of vertices Z1 and Z2, we consider all the simple paths from Z1 to Z2. Okay? And for each path, we're going to define a monomial, which is basically the product of variables associated to the edges on the path, and that's xp. And then we define xp tilde, which is a polynomial, which informally states that p is the shortest path between its endpoints. That is, you have a term xp, so the two endpoints are connected, and then we multiply for all paths q of smaller length by 1 minus xq. And then for vertices z1 and z2, we sum up these xp tilde over all paths from z1 to z2 that go through the vertex v. And we get one polynomial in the representation. And of course, the second one is just a sum over all paths from z1 to z2. And now between centrality is obtained by adding up all these fractions. So this is a sketch of the proof that between centrality is indeed a rational centrality measure. So why are rational centrality measures, decent representation of the family of natural restrictions? And the reason is that there are multiple things that we can code that will yield rational centrality measures. For sure, if we start with the coalitional scale games with rational coefficients, then this Shapley value will be a rational function. We prove that. But we have the following definition, which states that if the value of a coalition depends in a simple way on the graph structure, and again, simple we mean rational, then as we're going to see, this is another case where we get rational centrality measures. So what do we have here? We want the value of a coalition S to be represented as a ratio of two polynomials, Pn and Qn, Of course, now the polynomials need to take into account both the edge structure and the vertex structure. In other words, we have one set of variables for all the potential edges and the other set of variables for all the potential vertices, and we basically set those to 1. Okay, so a characteristic function is called rational if we could be represented as the quotient of two polynomials with rational coefficients in this form. Okay. And indeed, we prove that if this is the case, then the resulting Shapley value of the game is a rational centrality measure. Just as an application here, I gave you the representation of the characteristic function for game theoretic network centrality. And as an application of the previous result, game theoretic network centrality is a rational centrality measure, as we saw. So, in conclusion, we've identified some family, which is quite natural, which yields rational centralities, and which includes between a centrality, degree centrality, game theoretic network centrality, and which to a certain extent captures the idea that the value of the coalition depends simply on the network topology, and we don't do something very adaptive like we did in our previous result. But eigenvector centrality is not rational in this sense. And it's an interesting open question how to extend the class of coalitional skill games to capture eigenvector centrality as well, and maybe other natural centrality measures which are not represented in this framework, representable. We're now going to switch gears, and I'm going to give you a discussion of one phenomenon that we're able to model using our coalitional skill game framework for network centrality, and that's the notion of helping. And let me motivate this by an example that we're all familiar with. We may serve on program committees of conferences, and you get papers, and each paper needs to ultimately have at least 3 reviews. And you may not be able to read all the papers you are assigned, but you can use help sub-reviewers. And of course, you are a valuable member of the program committee if your friends can be enlisted as sub-reviewers to complete the task of getting these reviews done. So basically, having a lot of competent friends can compensate for the fact that you may not be able to read all the papers that you are, assigned. So this is the notion of helping. I remind you its extent to which a node may be able, another coalition, to accomplish some tasks, not by its skills, but by the skills of its neighbors. Okay? And the question is, how do we model this? How do we measure how helping a node is in a network, in this sense? And before giving us our solution, let me show you in brief a couple of ideas that don't work. So the first and probably most obvious thing we could try is to use some sort of Shapley value or combination of Shapley values of some coalitional games. For instance, if we start with some game NV on a network, let's consider the helping extension of this game where the value of a coalition S is the value of S plus all its neighbors. It's the idea that we wanted to encode in helping. And we could try to define the helping centrality of a node as a difference between the Shapley value of this helping extension minus Shapley value of the original game. This doesn't work because this measure will assume negative values for some nodes. And intuitively, that's bad because we want to, measure helping at worst, a node will be unhelpful. It doesn't, its neighbors will not be able to help the coalition. But normally it shouldn't hurt. The more people you add to a coalition, the more skills they have. So we don't expect that a node would hurt in this helping sense. So having a negative value is non-intuitive, and this doesn't work. Now, there is another version of this idea, and this looked very promising initially, but it also doesn't work. And to motivate this, let me consider the following simple coalitional game, where each node has a weight W of I, and the value of a coalition is simply the sum of weights of the nodes in the coalition. That is, it's a weighted dummy game. Now, if you compute the Shapley value of this game, then there is a simple formula for it, and it has sum, one part which involves the node Z, and another part which involves the neighbors of node Z. So if we want to disentangle the actual contribution of Z's skills to helping a coalition, we should basically subtract the first term, which is 1 over a degree of Z plus 1 times the Shapley value. So this would suggest that rather than subtracting the Shapley value directly, we should subtract this appropriately scaled version of the Shapley value. And this doesn't work either, because there are some natural games where this gives negative values. Okay. So what's our approach for measuring helping centrality? I'm going to give you two measures. One which is actually not disentangling the contribution of Z, and the second one will do that. So the first notion is called helping Shapley value, and it has a formula which is highly reminiscent of the ordinary Shapley value, except that rather than only adding I in the marginal contribution, we also add all the neighbors of I, and the skills, of course, added by those. So this basically generalizes the Shapley value, because for the graph, which is a bunch of disconnected nodes, this reduces to the ordinary Shapley value. But it's not really a general, it cannot be represented as a version of the Shapley value directly. It has some properties which are nice. For instance, centralities like this defined are non-negative for monotone games. Not all things are nice. Centralities don't add up to 1 or V of n in this sense. Just as the Shapley value in terms of computational properties, it's sharply complete because it's sharply complete for the Shapley value. But if you add some extra restrictions like the ones that we had in the previous result, then you can compute it in fixed parameter polynomial time. Okay, so for some classes of coalitional scale games, you can compute it. So this notion, again, measures the contribution of I plus its neighbors. It's not only the contribution of the neighbors, but also of node I. So to come up with a notion that disentangles the contribution of skills added by node I from those added by the neighbors, we come up with a second measure called helping centrality. And it has a similar formula, except that we subtract also the skills added by node I. And as you can see, helping centrality is very closely related to the helping Shapley value by the green formula there. Basically, the helping centrality is a helping Shapley value minus the ordinary Shapley value. There are other things in the paper that suggest that this is a notion that is sort of on the right track. For instance, there is a so-called Vito decomposition via Harshani coefficients for the Shapley value. There is a formula like that for helping centrality. And helping centrality and helping Shapley value can be computed under some natural restrictions on the game. So I'm summarizing here what's happening with the two centrality measures. So let me show you these measures on the particular case of the game that I've described before. I remind you that a coalition gets a value of 1 if it contains two nodes with martial art, that is two yellow nodes, and one node which is a pilot. Okay, so this is helping centrality. I'm going to first flash here the computations of helping Shapley value, helping centrality, and the ordinary Shapley value for this network. I should say that computing the helping Shapley value and helping centrality seems of the similar complexity in practice as the Shapley value. So probably we haven't really done this in the paper, but it's an interesting problem to extend the efficient techniques for the Shapley value to these new measures. Let me discuss these results, these tables, in the slides that come. The first thing that I want to say before talking about interpreting results is the following. There is a natural notion of two nodes being equivalent, and that notion is the following. Two nodes are equivalent if they have the same skills and their neighbors have the same multi-set of skills, identical as multi-sets. Maybe not necessarily distributed in the same way, but overall, their neighbors can do the same things. Obviously, two such nodes will have equal values for Shapley value, helping centrality, helping Shapley value. So basically, this notion of equivalence is partitioning the set of vertices into equivalence classes, and we only need to compute one value once per node. And let's look at that for the Shapley value. So the Shapley value is about what the abilities of one node are bringing to the table, which means that we're actually going to have three settings. The pilots will have one class of values. People that know martial arts will have another class of values, and people that have no skill will have another one. And what Shapley value tells us is something that's natural but not necessarily very informative. It tells us that being a pilot is more valuable than knowing martial arts, which is more valuable than having no skill, with respect to how much a node is able to help by its own skills. What about helping Shapley value? Well, what's happening there is that we get an ordering of vertices, and basically here, the three of the pilots, nodes 7, 9, and 12, are the most helpful nodes, and the node 2 is the least helpful one. And node 2 is the least helpful one basically because it has one skill, which is a pilot, which is knows martial arts, but its neighbors don't bring anything. So if you look closely to the network, every single other node in this network will have the property of bringing at least this much to the table when considering the contribution of the node plus its neighbors. Okay, so node 2 is the least helpful. And the three pilot nodes, 7, 9, and 12, are the most helpful. But again, in helping Shapley value, we're conflating the skill of these nodes, which is valuable because we've seen before they're pilots, and this is the most valuable skill they may have, with the skills brought by their neighbors. And if you look closely, every such node would assemble a winning coalition by itself and its neighbors. Okay, so the difference between node 5 in node 7, 9, and 12 is that node 5 doesn't have enough yellow nodes to have a coalition with value 1, whereas the other ones have. So this is natural that these nodes are the most helpful with respect to helping Shapley value. But again, in this measure, we're measuring the skills of the node plus the skills of the neighbors. What happens if we disentangle this and we look at helping centrality, which only concentrates on the skills of the neighbors? And basically the picture changes quite a bit. So now the node that is most helpful is node 16, which doesn't have any skill of its own, but has enough neighbors that it could assemble a coalition which could carry an attack. So node 16 has the highest helping centrality in this sense. Also, node 13 has a higher value than the other ones because, yes, the other ones are more valuable with their own skill, but this is counterbalanced by the fact that their skill is valuable in this sense. So in a certain sense, they only bring extra yellow nodes by their neighbors, whereas 13 brings a pilot, which is more valuable. Okay, so this is sort of the intuition for the change. And again, node 2 is the least helpful one. So there are many, many, many issues and open questions that our work has raised. Of course, one could, for instance, try to see if one could use other succinct game representation frameworks to represent centrality measures and many other things. I would be willing to discuss this with you and hope this was interesting. If you have any questions, please email me at this address. Thank you.